Hello, physics students. This is Mr. Williams here. I am here coming at you today to introduce a couple different ideas to you and really introduce this concept of physics and then go through and maybe define just a few vocabulary words to get us started and get the ball rolling as we transition into the study of this crazy, magnificent, huge, outrageous concept that is science. So let's go ahead and get started. Now, physics, the class that you are taking, where you find yourself right now, is the study of matter and its motion through space-time. So that's as simple as I can really put it, that we study stuff and how that stuff moves. We look at how and why matter gains properties like it does. So we know that this stuff can have different properties. Some stuff is hard, some stuff is soft, some is hot, some is cold, some stuff is able to explode while others is not. Looking at those properties of like molecules, of like that molecular interaction, that goes into chemistry. We're looking at more large scale here. Why does a moving car have the ability to break a tree? Why does the sun have the ability to feed our entire planet energy? And how is that energy move? How does that energy get harnessed and the motion of energy go from one object to another? So physics is really the most fundamental science because, and all the things I just said right there, you could talk about chemistry, ecology, biology, we can talk about geology. All of that has properties in physics because we want to just look at the most fundamental ideas and just describe how the whole universe behaves. And that is physics in a nutshell. So the scientific method is something I'm sure you guys have heard of before. We've seen a bit, you probably first heard about it, I don't know, third grade or something. It's really important for us to realize, especially at your age now, that science is not a book of facts about the world. And that's so much of a common misconception about what science is. And I think a lot of that comes from how you're educated. That as we go through and teach you these things about ecology and these things about biology and chemistry, we just are spitting facts at you of things that we now find to be true and making you memorize it. But that's not what science is. Science is a way to understand the world. And now there are so many things that we do know to be fact because of our tried and true practices of the scientific method. So when I spit facts at you, these are not just like facts from a book because the book in this book just holds all truth. Any science textbook you get is not just infallible. It's instead the things that we think are true about the world, and we have good reason to believe them because we've gone through the processes of observation and experimentation. We observe and we experiment and we test and we apply good rational thinking to this experimentation. And that's all that science is. Observation, experimentation. Now, exactly how those are done could be on a totally different kinds of processes, depending on your science, depending on your field, depending on what you're trying to study. But boils down to the basics of observation and experimentation. And we learn from them. The scientific method, you might have seen it written another way. Observe, infer, and hypothesize, test, conclude. We're saying the same thing here. The scientific method is how we can learn about the world on so many different scales. We are going to use this in our classroom to just study the motion of various objects and the properties of which they have. But we can study also how it's already been done, how different scientists have done this, and what conclusions they came to, and how are you in terms of physics, the conclusion we come to are often bigger because when we study the entire universe, we make really big and exciting discoveries about about rules that govern everything, which is crazy. I'm going to post a link in this video that goes over the difference between a scientific law and a scientific theory. It's often misunderstood, and I'd like you to watch this video, and you can do that after this lecture. All right. So making measurements. Physics and any science is all about observation, and taking measurements is so key here. Without taking measurements, how could we learn anything about like our actual world? Like I could just throw out numbers to you, but numbers mean nothing unless like you actually measure. Imagine if you want to build a house and you're not going to do that by making any measurements. You can sketch something out and then you got to measure, and then you have to interpolate what a certain measurement means. It means a lot if something is 2 inches versus 2 miles. Meaning comes from these measurements, and anything that can be measured, I give the blanket term of physical quantity. And I'm going to use this a lot, and sometimes you might forget what this means, but think about just what this sounds like. A quantity is just a number, and physical just means like physically in the world, like actually exists. And so a physical quantity is just a number that exists. And more specifically, I can't sure, the number 3 exists, but if something is 3 feet long, well, then that relates to something. So it's a measurement about a physical thing is a physical quantity. And this could be any speed, temperature, mass. There's so many different ways to measure objects. And so speaking of measuring objects, different objects have different types of properties, and we could really boil this down into 2 different types: intrinsic versus extrinsic. Mass is the amount of matter in an object. If I have an apple, let me try to draw myself an apple here. That's the best I got. Apple. Think about mass is just like how many atoms are inside of this apple, right? All objects are made up of atoms, and there is a very finite number of atoms in said apple. Mass is just a measurement of that. How many atoms make up an object? That is an intrinsic property. If I can't change the number of atoms that make up the object without changing the apple itself, if I cut it in half, does the apple have now half as many atoms as it did before? Well, no, I just split it in half. Half of the atoms are on one side and half of them are in the other. So mass is this intrinsic thing. An apple is what it is, and you can't change that. But the weight of that apple is different. Weight is a different measurement from mass, and we're going to see this a lot in our next unit, or in our 3rd unit on forces, that it is how much force the mass is pulling down with. And that comes from gravity, right? All things fall towards the ground. And we'll talk about why that is later. And it is proportional to the mass. Bigger objects do pull down harder. But I could change the weight without changing the object itself by just moving it to a different location. So an extrinsic property depends on the location or the environment in which something is in. If I bring this apple to the moon, it's going to weigh significantly less because the moon does not pull down as hard as the Earth does. So intrinsic properties versus extrinsic properties. These are different kinds of objects or different kinds of properties we can measure for objects. We are almost to the end here. Last thing I want to talk about is dimensions and units, which is really how we measure things. The dimension of a physical quantity refers to the type of quantity it is. And surprisingly, there are few dimensions. So the unit then on the flip side, these unit and dimension are very similar quantities. Dimension is more of big picture. Unit is specific. So if I want you to measure the length of something, that is a dimension. That's a kind of way you can measure something. But how you choose to measure that length is going to take a unit. And so I put the example here, 1.45 miles and 0.36 inches are the same dimension. Both are measuring length, but they are different units. Why do we need these units? Why can't I just have a standard length measurement system? Well, as we can see here with these 2 different lengths, these are very large differences in the size of things. So different units are better for different scales. And why we use units at all is so we can all agree on a standardization practice. If everybody watching this understands about what 1 inch is, then it means something to you when somebody measures something to be 4 inches or 12 inches. And the same goes with miles. And you might not have a perfect understanding of a mile, but you know it's long. You know about what it means. If I tell you to walk a mile, you know about how long that would take. If I tell you to walk 10 miles, that's going to be significantly longer. And so that's why we have units, to be specific about how something is measured. And they're just a human invention so we can share a measurement with each other. But the dimension, again, bigger picture, is the type of way we can measure something. Seconds and years are the same dimension. We call that dimension time. We already went through the first one and called it length. And the last one, 400 tons and 35 grams, is the same dimension of mass. And these three dimensions are really like it. And we call them the three main base units, the three most likely things we're going to make a measurement of: length, time, and mass. And crazily enough, it's like, well, there's so many other things you can measure, right? Well, yeah, but they're just combinations of these things. Energy or speed is just a distance divided by time. When you say how fast is your car moving, it's 20 miles per hour. It's a 20 length over time. If I measure the force of something, how hard something hits, well, that is just, it's a combination of all three. Mass, how much mass you are delivering in a certain amount of distance over a certain time factor squared. We will see throughout the whole course how we're going to combine these together, but the main things, these are the three main base units. And you can see here, I accompanied them with the units that I'd like. So these are the three, what I've underlined right now are the three main base dimensions: length, time, and mass. We can measure those dimensions in several different ways, but I provided for you in blue now the units that we should be measuring these things in: meter, second, and mass. To give you some perspective, a meter is about 3 feet. A second is a second. You know what a second is. And a kilogram is about 2.2 pounds. Now, why don't I use feet and pounds? You guys are probably more familiar with those quantities. Well, that brings us into SI units. Scientists use SI units because it has two really big advantages. One, everyone measures things the same way across the entire world. Literally every other country measures things in meters, in kilograms, in seconds, because that's the smart thing to do. America sits here on its lonely little island saying, no, but it makes so much more sense to have 5,280 feet in a mile because everybody can remember that. Well, it doesn't, but we are doing what we are. But in our class, we are going to use SI units because we are learning to be scientists here. And the second is because the metric system operates on that base 10 scale. So converting makes things so much easier. So just like how I said, there is 5,280 feet equal in 1 mile. And you have to remember this. It's way easier to just remember how many centimeters are in a meter. Oh, well, a centimeter is 1/100th of a meter. And so there are 100 centimeters in a meter. Or how many meters does it take to make a kilometer? Well, a kilometer is 1,000 meters. And so you'd have to go 1,000 meters before you hit 1 kilometer. It's way easier to use these metric units, and we will get practice doing it through this whole course. All right, that was everything that I wanted to go over today. Our next video is going to be on converting units and using conversion factors to do that. We will hit that